Okay, so thank you very much for the invitation and the introduction. It's always a pleasure to be here at the Schrödinger Institute in Vienna. And what I'm going to present today is some review of basic facts, mainly on, say, a sort of functional analytic type concerning the construction of the Cheeger energy and its duality properties in a setting which allows for extended metrics and so covers quite general examples. So these results cover contribution we did some years ago with Matthias, Erbar, and Luigi Ambrosio, and then still with Luigi Ambrosio and myself, and also refers to the theory we developed with Luigi and Nicola on this class of spaces. So let me first start with the definition of extended metric topological space. The question is, the basic starting point is that you have a set X and a metric D, but the metric D satisfies all the axiom of a metric, but can also be extended value. So D maps X, Cartesian X, to 0 plus infinity. So can take the value plus infinity. All the other axioms are the same. And in particular, the space X with D perhaps is not separable, has bad topological properties if you want to put a measure in XD. So the idea is to introduce also a sort of auxiliary topology, tau. So tau is a topology on X, and these two objects have to satisfy some compatibility properties, and the compatibility properties concern the class of Lipschitz functions, which are d-Lipschitz with respect to the metric and continuous with respect to the topology tau. So I will denote by lip B, since they are bounded, x, d, tau, such class of functions. So d-Lipschitz and tau continuous. And this is the natural algebra of functions that you want to use to construct the Cheeger energy. And what are the two compatibility properties? The first one tells us that this set contains enough functions to characterize the topology tau. So this is the topological condition. So the tau is generated by such class of functions. This means that if you have a net, since in general, of course, you may think that tau is a polished or is a good topology, so perhaps sequences are sufficient, but if you want to work in general, you have to use nets. Say that in the case of sequences, a sequence is converging if and only if, so xi is converging to x, if and only if f of xi is converging to f of x for every f in your algebra of bounded and the Lipschitz functions. So this is the, let's say, topological compatibility, and the metric compatibility, you can recover the distance d, the metric d, from this set. So for every x and y in x, you have that the distance between x and y is the supremum of fx minus fy among all, say, f in lip b1 x d tau, where 1 means that the function are 1 Lipschitz, of course, since you have these quantities always bounded by the metric. Okay, so there is these two topological condition. This set should be sufficiently rich to recover the metric, and also to recover the topology. And there is this interplay. There are two equivalent formulations of these properties. One is in terms of family of continuous. Of course, there is a very natural case when tau is the topology induced by D. Perhaps D is a Polish space, you can use tau as the topology induced by D. In this case, of course, these two conditions are trivial. The more interesting case is when D is obtained as a supremum of tau continuous D semi-matrix. So this condition is equivalent to say there exists a, let's say, directed family of metrics, which are now real metrics. You don't ask that they are semi-metrics, so perhaps they vanish also on different points, but they satisfy the triangular inequality. So I is indexed by some directed set, capital I. Di are monotone with respect to I, the order in I, and di are tau continuous semi-metric, and moreover, d of xy is just the supremum with respect to I of this di of xy. So you may think that di is the standard case where the topology coincides with the metric, and you are generating D by an increasing family of metrics, okay? And this, of course, since you have no controls on these metrics, perhaps ends up with a function which takes plus infinity. Moreover, let me also comment that inside these two compatibility conditions, also you see clearly also from here and also from here, the metric D necessarily is tau lower semi-continuous, and moreover, the topology tau is induced by a family of functions, so the space is completely regular, which is quite important for studying weak convergence of probability measures. And yes? No, that is not. It's out. It separates the point. And there is another important point here that perhaps you, and another object which is interesting to use is perhaps tau is generated by an algebra A. So you have A, an algebra included in lip B x d tau. So a good algebra of functions. Of course, you can always choose as an algebra all the Lipschitz functions, but you may select a best set, and then you may ask these two conditions just restricted to A instead of lip here. So in practice, you want to replace all the Lipschitz function by a subclass, and the conditions are still that this class is sufficiently rich to characterize tau topology and to generate the metric D. Okay. You want to? No. It's an algebra, given algebra. Of course, you can always take the closure with respect to the sup distance, but this is not needed. In fact, this is an algebra of Lipschitz function. So taking the closure, you may lose the Lipschitz property. Okay, and of course, you want to, since of course we do not assume to force the one property, the one Lipschitz constant. And usually you have also to play with a measure, a reference measure. So M now is a positive finite measure with respect to the topology tau, not with respect to the metric D, and we will assume that is a radon measure. Radon means that for every Borel set B, with respect to the tau topology, the measure of B is the supremum of the measure of K for every K compact included in B. This condition is for free if tau is a Polish topology, or a Lusin or Suslin, whatever you want. In general, if you don't assume anything about tau, you have to add this radon property. Otherwise, it's very difficult to do any construction, okay? And, okay, so if you have this assumption, I will say that X, which is the system of extended metric, topology, and measure, is an extended metric topological measure space. Okay, these are the abstract setting. And what is interesting, and A is an algebra which is compatible with X. Okay. I will introduce completeness later on. Up to now is not needed. Of course, when we will introduce the Cheeger energy, we will see that for the strong form of definition of the Cheeger energy is invariant for completion. So it is natural to use some completeness. Okay, so examples of this setting. Clearly, as I already mentioned, an interesting example, the simplest example, even still interesting, is the case when XD is already separable and complete, perhaps. And in this case, you select tau as the natural topology, but there are interesting situations where tau can also be different in that setting. For instance, consider the case where X is a separable Banach space. Okay, so in this case, there is no need in principle to introduce a topology, but perhaps you want to use as A the set of cylinder function. So cylinder functions are just functions of the form psi of say phi 1x, phi 2x, phi dx, where psi is say C1 bounded, and phi I are element of the dual of X. Okay, this is a nice algebra that you want to use in a Banach space, natural algebra, since it's easy to do computations with this algebra. And if you immediately see, since the function depends inside the psi in a linear way from X, this algebra generates the weak topology of B and not the strong topology. Okay, so in this case, it's natural to think to the weak topology of B. Another more, let's say, variant of this example is when you have another Banach space included in X with a norm stronger than X, and you assume that the norm of V, this map, let's say N of V, which is the V norm of V if V is in V, and plus infinity if V is not in V. This is lower semi-continuous, is lower semi-continuous in X. So in this situation, I will use as tau the strong topology of X, and I will define as extended distance between 2 points in X, the norm of X minus Y, where this quantity, if X minus Y are in V, otherwise it's plus infinity. This is the, let's say, the Wiener example modeled on classical Wiener spaces for this situation. And usually the probability, the finite measure M is a Radon measure, X is separable, so it's a Borel measure in X. Okay? This is a typical example of this situation. And you see that in this case, D is not separable since it takes plus infinity in a huge set of X, Cartesian X. Okay, and another interesting example, which is motivated by the study of the Wasserstein space, is the following. You may take as X the space of probability measure in RD, for instance, but here you may take other spaces. And with the weak topology, tau is the weak topology. And as a metric D between two measures, you select your preferred Wasserstein metric induced by for instance, the Euclidean metric on RD. So, for instance, W2 of mu nu. If mu and nu have finite metric, this, of course, for arbitrary measure, you have no controls on the second moment of the measures. This can take a value plus infinity in a huge set. So this is a very natural example, and in this class, you can reproduce the class of cylinder functions in exactly in the same way. Here, the duality are just, all these terms are just integral of phi with respect to mu. X is now mu. The linearity is this form, and this phi I will be C1 bounded function on RD. Okay, so there is a natural algebra here, the algebra of cylinder function, a natural weak topology, and a natural metric. And this represents the typical setting, of course, depending on the measure. For instance, you may consider the many measures on T. For instance, the measure studied by Theo or Lorenzo, the Ferguson measure, and others. Okay, so in these settings, you have this particular situation. Okay, so these are the example. Now I want to construct a Cheeger energy on this framework. How can we proceed? The construction is quite the same. The idea is that you replace the space of Lipschitz functions by your algebra A. Okay. So first of all, you define for every f in the class of Lipschitz continuous functions, the asymptotic Lipschitz constant in X, which is the infimum of the Lipschitz constant of f in a set U, where U is a neighborhood of X in the tau topology, so is tau open, and U contains X. Okay. So by construction, so you consider the Lipschitz function, the Lipschitz constant of f restricted to U, and you take the infimum with respect to all the possible neighborhoods of X in the tau topology. So by construction, this object is tau upper semicontinuous. So the f A of X is tau upper semi-continuous. So as good measurability properties with respect to tau. And then you now restrict this object to the class, your algebra, and you consider what we call the pre-Cheeger energy. We fix a P in 1 infinity, as usual. So P is between 1 and plus infinity, 1 excluded in this setting. So the pre-Cheeger energy is just the integral of this upper semi-continuous function with respect to M. And this is a nice convex p-homogeneous function restricted to the algebra A, if f is in A. If A is all the Lipschitz function, you have the usual pre-Cheeger. Otherwise, it is defined only on the algebra and clearly is plus infinity if f is not in A. And then, starting from this object, you construct the LP relaxation, so the Cheeger energy now of f is just the inf of the liminf when n goes to infinity of the pre-Cheeger energy of Fn, where among all the sequence Fn in the algebra A converging to F in LP, P with respect to the measure M. Okay, this is the. No, I'm excluding one. And then you have an object. Here you use in an important way the fact that A is an algebra to construct a local object. And this local, what I should write here, in fact, the Cheeger energy depending on P and also on A. Okay, depends on all the structure in principle of your space, so the topology and the algebra. F is in LP. So F is a reasonable function. Okay, and I will not express the dependence of the Cheeger energy on these objects, since we will see that at the end it will not depend on these objects. This is an interesting property. But in principle, I should write here that depends on A. So if I want to stress, I will add at least the algebra. But also the topology, since the topology characterizes this object here. Later, we will see that it does not depend. Say that you have all the interest to select a weaker topology tau, and a smaller algebra, of course, since you have less objects to deal with, better properties, and there is a sort of competition. And until you are in the framework that the algebra is sufficiently rich to characterize topology and metric, you will have this object. And this object has representation in terms of a relaxed slope, so you may also write this as the integral of the relaxed slope of f with respect to m, and also this relaxed, the minimal weak upper gradient, also in principle depends on A. Okay, and also on M, clearly, or everything here on X. So everything here depends on this X here. And you can define the strong, say, Sobolev space, which depends now on all the objects, which is just the domain of the Cheeger energy. so the set of F in LP, such that the Cheeger energy of F is finite, and we can put in this domain the norm, which is the P root of this quantity. I will use also later on this expression where I add a parameter kappa, is just the Cheeger energy of F plus K, the LP norm of F to the power P, and the norm here of F in H1P is just this modified Cheeger energy with kappa equal 1 to the power 1 over P. Okay, this is a Banach space. Now we have some questions. How this object depends on the topology, how this object depends on A, and other questions. And we have good results at this respect. So first, say that first result is that the Cheeger energy is independent of tau. So if tau prime, tau second are compatible topologies, then the Cheeger energy of F, let's say constructed with tau prime, is the Cheeger energy of F constructed with tau second. So it really does not depend on the topology. Yeah. Yeah. By construction. The second property is that the Cheeger energy does not depend on the algebra. This is a sort of density result. So the Cheeger energy constructed starting from an algebra A of F coincide with the Cheeger energy constructed from all the algebra of bounded Lipschitz function tau continuous. So it is invariant, this construction, with respect to the topology. Say that this can also be rephrased in a sort of as a sort of density result. If I start with this, the largest possible algebra, then this means that every function for which this is finite can be approximated by function in the algebra, such that this construction here, the Lie-Minf of this object, converges to this, in principle, lower quantity. Okay? And there is a more general framework for stating these two properties. The more general framework is considering general embedding. Perhaps I don't insist on this. So you consider immersion embeddings, which are isometries with respect to D, which preserves the measures and are continuous with respect to the topology. The Cheeger energy is invariant with respect to this class of transformation. An interesting consequence of this invariance is that you may always replace X with, you can always embed X in a complete space, which is D-complete, and the Cheeger energy does not change. So you can start from X, you take a completion. The completion is not immediately clear how, since you have to deal also with the topology, but this is possible. And the Cheeger energy is invariant with respect to completion. Moreover, you can also embed X in a compact space, and the Cheeger energy is invariant with respect to compactification. So it is interesting that you can always embed in a, say, situation where you have a new space with a new metric, a new topology, and a new measure, which is isomorphic so let's say for which there is a measure preserving isometric and continuous embedding, such that x tau is compact. So is not restrictive if you want to prove general properties on these spaces to suppose that the space x tau is compact. This is quite useful. In this case, it's useful not to restrict to Polish topologies, since the construction perhaps produces a space which is not Polish but is still compact, okay, with a radon measure, etc. Of course, if A contains a countable set which generates the topology, then tau hat can be selected as a Polish topology. In general, no. Yeah. This is really inspired by the constructor of Fukushima, where you use the algebra and you embed X in the space of characters with respect to the algebra. This is very useful to have this algebra. And in practice, you can always assume, in this case, that your X, in fact, is a subset of a convex, compact set of the dual of the algebra A. And is contained in the set of convex compact of the unit ball of the dual of the algebra, and coincide with the characters on your algebra. So you can always embed your space in a vector situation where, in principle, you can use the vector structure of X. Okay, and say that there are other interesting properties. The fifth one is that if you replace D with another distance, d prime, which is bounded by the length distance generated by D, and the length distance is obtained by taking the infimum of the length of path connecting two points. In general, the length distance, even if you start from D, which is a finite metric, this usually can take plus infinity. And if D prime is compatible with respect to the topology tau, then the Cheeger energy associated to D prime coincide with the Cheeger energy generated by D. So this construction is invariant with respect to taking the length distance if the length distance is compatible with respect to the topology, or if you take intermediate distance which is compatible. Yes? Yeah. So for me, finite means that there is a Lipschitz parametrization with respect to the metric D. You don't see the topology tau here. And there is also the identification, say, of this space with the Newtonian Sobolev space added by Mungalligan and based on the notion of upper gradient introduced by Cheeger, Kosker, and McManus. Okay, this is a general result of this construction. And in particular, thinking that the Newtonian construction is naturally related to the length distance, this property 5 is not surprising at all. Okay. Yes. Yeah. Okay, sorry. Okay, and now I want to spend the last 10 minutes to present duality. So we have seen this class of properties. What can we say about duality? And I think that this is interesting since presents a different way to use dynamic plans, so plans on the space of path in X, which is quite interesting in this setting. So what does it mean, duality? We have now a Banach space, and we can construct the dual. So I will define H minus 1 Q of X, the dual of H1P of X. Okay, is a dual of a Banach space. We have to be careful since clearly H1P is continuously embedded in LP, so LQ is continuously embedded in this dual. But in general, even if this is dense, this exclusion may not be dense in general, since we don't have any reflexivity here. Okay? I forgot to say that using this identification, if we are one of the nice application of this result is that if we know that the pre-Cheeger energy associated with the algebra A is satisfy the parallelogram rule, or it is uniformly convex, then for free, using this density, we have that the Cheeger energy has the same property, and in particular, you gain the fact that the space H1P is Hilbert in the case P equal 2, or uniformly convex, so reflexive in the general P. Okay, so, but in general, we don't have density here, so we have seen that an important space that we called H minus 1Q PD of X is just the closure of LQ in H minus 1Q. Okay, so this is a closed subspace of this space. And there is another important, another interesting object is if you, instead of starting from the Cheeger energy, you want to start from the pre-Cheeger energy, so without taking this Lim-inf, you just work on the algebra A with this object, which is still a convex function, then you may consider this space AQ prime, which is the space of L, which are bounded and continuous with respect to the algebra, so are dual with respect to the algebra, where I put the pre-Cheeger energy P as a norm, and with a further condition that for every sequence of equibounded pre-Cheeger energy in A, such that the pre-Cheeger energy is bounded and Fn is converging to 0 in LP, then you have that Lfn is converging to 0 as well. So it's a subclass of functionals on the algebra which behaves well with respect to the pre-Cheeger energy. Okay? And what we have, a class of result. So the message is that the good space to work with is this one. And this one can be identified with this one. Okay, why? Since at this level, you have the following properties that, first of all, say that you can, every function L in AQ prime, so which satisfies this condition, can be associated in a unique way to a unique L in H minus 1Q PD. So you can extend a function just knowing its effect on the algebra to a functional in the dual space if it satisfies this condition. And moreover, you may define for functions in this H minus 1Q PD, you may define, in general, in fact, you may define the dual of the Cheeger energies. So you can define these objects of L. I write in this way, 1 over Q. They are just the dual of the K Cheeger energy. Sup with respect to F. Okay, so they are Q homogeneous functional. They are dual of a P homogeneous functional, and with respect to K. And the same way, I can also define the dual of the Cheeger energy just by removing K. And you see that this is equivalent to minimize this functional. And if you are in this space, this is as an optimum. So there exists for every L in H minus 1 Q of X, there exists a unique U, say QK of L, satisfying the minimum, minimizing this, the negative of the opposite of this functional. So minimizing 1 over P, the Cheeger energy K of U minus L U. And notice that this corresponds to a sort of nonlinear equation in the Sobolev space, since this U satisfied by, should satisfy this equation. Where A is the subdifferential, so the nonlinear Laplacian associated to the Cheeger energy, this is the duality mapping LP, and this is L. In general, if you start from an arbitrary dual element, you are not sure that you can satisfy, you find a unique solution, but if you start from this restricted space, L minus 1 QPD, then you have a solution. And the last property, which could be interesting, is that if, two properties, if L is a dual element of your algebra, AP, and L is positive in the sense that LF is non-negative for every F non-negative, then L is an element of the space. L is in H minus 1 Q of X. So you may solve this problem. And finally, you have that H1P of X is the dual of H minus 1 Q of X. PD. So our original Sobolev space has a predual, which is exactly 1. And let me conclude with this. Now you want really to represent perhaps how this dual of the Cheeger energy is. So how to represent this dual, say L, and not for a general L, but for a positive L. And you may guess that a positive L can be represented by a probability measure, a positive measure. So I suppose that mu is a positive measure in X. And I want to, let's say, let me write in this way. I want to represent the dual of the Cheeger energy associated to the difference of two positive measures such that this object is finite. And there is this nice representation. This object can be really characterized in terms of superposition of path. And in this way, let me conclude with this representation. You start, let me call Ra of X the space of all the rectifiable path with finite length in X. And we can associate to every gamma which is, you may think that the gamma is represented by its Lipschitz parametrization. You can associate it to every gamma the integral with respect to gamma of a function f, which is just the integral, if you choose a parametrization between 0 and 1, of f of gamma t, gamma dot t dt, assuming that gamma is d Lipschitz. And now you put a measure here. A dynamic plan is just a probability, positive radon measure on this space, such that if you denote by L of gamma just the length of gamma, and such a measure is a dynamic plan if the integral of the length of all the curves with respect to gamma is finite. If this integral is finite, then you may associate a unique measure that is a sort of barycentric measure associated to pi. Sorry, I'm going quickly here just to conclude, which is just, which is defined by this dual relation. The integral with respect to this measure is just obtained by superimposing the integral of f with respect to, of h with respect to gamma, and then integrating with respect to p gamma, okay? Fine, and we say that pi has a finite q barycenter, so bar q of pi is just the LQ entropy of this barycentric measure. So d mu pi with respect to dm to the power q in dm, plus infinity if mu pi is not absolutely continuous. So you are really representing pi as a superposition of path. The integral with respect to this path has to be absolutely continuous with respect to your reference measure. Okay? Now you have this final representation of the dual of the Cheeger energy. You can prove that the dual of the Cheeger energy between two measures mu1 and mu0 is just the minimum, if it is finite, of this barycentric energy Q of the dynamic plan, where pi, of course, has to be a dynamic plan in this sense with finite barycentric energy, and has to have initial and final marginals exactly mu0 and mu1. So pi is a superposition of path. You can take the initial value, so mu0 is E0 sharp pi, mu1 is E1 sharp pi, and then you can represent this dual exactly as a family of paths connecting mu0 and mu1, such that the barycentric projection of pi has minimal Q energy, and you have an exact identity. So you may represent this thinking that you have mu0, mu1, and you want to connect all the points in the support of mu0 and mu1 by a family of paths in such a way that the integral with respect to this path behaves well with respect to the underlying measure, and you have this property. By the way, you, as a consequence of this identity, you will see that each path follows when you write the dual representation of this object, a gradient flows of the potential generated by mu0 and mu1. That is, let's say that this is a connection with another approach we used with Nicola and Ambrosio, using gradient flows to study in practice the duality and the equivalence of the Cheeger energy and the approach by dynamic parametrized plans. And here you still have duality, but for non-parametric plans, let's say. Okay, I'm stopping here. Thank you for your attention. and it follows by if you have completeness, it follows by this characterization that at the end all these paths coincide, all these approaches coincide with the Newtonian one, and so in principle, if you take where it is here, if you take just the local Lipschitz, but not the asymptotic one, you obtain an object which is lower. So it is easier to stay in this Sobolev space in some sense. So this, using the asymptotic one is more demanding, but if you have this density, or you may also see that on your algebra, these objects coincide, and then you define the same space. No, they have to be the same. Otherwise, this is plus infinity. No, 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 they are finite mass. Finite. Okay. Finite, and the same mass is implicit on the fact that this is finite. Otherwise, this quantity is infinite. Yeah, but if both are okay, you have to remove here the property that pi is a finite mass. So I don't know. It's not my job. Yeah. I don't know. I would say that a posteriori, the topology is just a useful tool. Since to deal with the measure, since probably it's easier to have radon properties of the measure with respect to the topology and to regularize the energy, but eventually you see that it does not play any role on the energy. So it's a sort of additional, let's say that this Cheeger construction is so stable that you can reinforce your approximating sequence, asking that the asymptotic Lipschitz constant is also tau upper semicontinuous. You can interpret this as a sort of regularity. You can also start, for instance, from what he said, but you can always find a better sequence for which Fn is in the algebra, and you can take the upper semicontinuous envelope of the local Lipschitz constant, provided the topology is compatible with the metric. Yes. Sorry, I didn't understand. The continuity with respect to tau. I would say that continuity is natural in this setting. Let's say that if you have two sets where you have metric, measure, topology, and algebra, it is quite natural that the algebra in the arriving set, say that I didn't write, but there is a compatibility property that if you have an algebra, say A prime in the arriving set, then I want that F prime composed immersion I is an element of the algebra A. This is not subjective in general, but still this compatibility. And I would say that if you have this property, then it's for free that the immersion is continuous if this algebra generates the topology of the target space. So I think that, yeah, you can drop the fact that the M is radon finite using some sigma finiteness or local moderate assumption. And then you have to replace the Lipschitz algebra with the locally Lipschitz functions, not uniform Lipschitz. I guess that this can be done. But I'm not sure. This is a good question. Say that you have some flexibility here. Whenever you can see in another way, you start, which is typical in the application. You have your metric and your metric, and you have an algebra of good function. The algebra should represent the metric, and then you can always take the topology generated by the algebra. So, and the crucial point now is that you have to see if your measure is a radon with respect to this topology. This is, say that in many situations it's natural to generate tau from A instead of the contrary. So there is some flexibility here. No, no, it's for free. Exactly, and you have this, the quasi-regularity of the Dirichlet form is obtained by the fact that you have this approximation by Lipschitz functions. And no, this is general. Thank you again.